Now we will start Laplace transform. Another topic, Laplace transform. So the prerequisite for it are improper integral. So if you are familiar with the improper integral, let me discuss. This is the function a to b f of x dx is said to be improper when either the upper limit or the lower limit or both of the limits are infinite. If you are looking at this integral, if either the lower limit or the upper limit is infinite or the lower limit is infinite or both of the limits are infinite, the integral is said to be improper integral. Or one other thing, if your function, this is the function, this function is undefined at one or more points of the interval. So the interval is 0 to 1. It means this function 1 over x square root. This is undefined at x is equal to 0. So I can write 1 over x minus a. For example, x square minus a square 0 to a dx. So these limits are finite, but this function 1 over x square minus a square is undefined at x is equal to a, which is the upper limit. So either the function is undefined at one or more points or the limits are one or both limits are infinite, then the integral are said to be improper integrals. Laplace transform, the prerequisites are improper integral, because in a minute I'll discuss what does a Laplace transform is. Let me have the introduction. So the word transform usually refers to certain device. That device may be electrical device, a mechanical device or mathematical device which converts an object of one form into another. So the word transform means to convert one object into another form. In mathematics, the word transform usually refers to a device. For example, if we were talking the Euler-Cauchy equation, in which we convert by using the transform x is equal to et. This is the transform we will use and to convert an Euler-Cauchy equation, which is a differential equation with variable coefficient, into an equation with constant coefficient by using this transform. So a transform means to convert an object of one form into another. In mathematics, we have this example, the Euler-Cauchy equation, which is a differential equation of the form, if I am writing x square y double dash plus x y dash minus equal to 0, let me have, for example. This is the Euler-Cauchy equation and the unknown function y double dash. It is going to be multiplied with the independent variable, the same power as the function's derivative is. Here the function derivative is 1, the independent variable is x. If I am going to write one more term there, so for the triple derivative I have to multiply with x cube and so on and so forth. This is the Euler-Cauchy equation in mathematics we use, and we convert this by using this transform. So eventually if you are using this transform, we convert this equation into constant coefficient, which is a cube y triple dash minus 2a2 y double dash, something like that. So the word transform means a device which converts one form into another. What does a Laplace transform do? A Laplace transform. So our topic is Laplace transform. Laplace transform converts an initial value problem. Into algebraic equation. So transforming to convert one form into another, like the Euler-Cauchy, you convert this Euler-Cauchy by using this transform into this differential equation. But what does Laplace? Laplace does and work with initial value problem, it converts into an algebraic equation. For example, if I am writing y double dash minus y0 is 1 and y prime 0 is 4, for example. This is an initial value problem because the conditions are function and on its derivative at the initial point. So Laplace transform converts this problem into algebraic equation, mean something like that, y minus 4s y something equal to 1. So this is sort of algebraic equation we are getting. So we are solving the algebraic equation, and by taking the inverse Laplace transform, we are finding the solution of this differential equation by taking the Laplace inverse. So Laplace transform converts an initial value problem into algebraic equation, means sort of algebra, something like that, and you solve the algebraic equation. Then by taking the Laplace inverse, you are finding the solution of the initial value problem. But one thing, suppose I am writing here et, or I am writing sine t or cos t or something like exponential, the polynomials. So we will just finish the differential equation in which this is non-homogeneous differential equation, and we are finding two solutions. One is the complementary function, one is the particular integral. We are adding them together and getting the general solution. If we were solving by using the ordinary differential equation, why we are having the Laplace transform? If we were like this, we were solving by C, D, the homogeneous part and the D operator, and then by P we were finding. So we are writing down the general solution by adding these two, and then we determine the constant by applying this condition on the at the initial point. Then why we are having Laplace transform? Laplace transform is well suited for the problem when the functions are piecewise continuous. Because if you remember, this is a continuous function. If I am writing a polynomial there at x square minus 4x plus 1, a polynomial are continuous function. If I am writing sine x or cos x, those are continuous function. But let me have, this is t. T lies between 0 and 1 because the independent variable is time this time, and y0 is 1 and y prime 0 is 1. For example, I am taking this at the moment. Now this t, which is the input function or the forcing function, it lies in this interval. After that it is going to be 0. T greater than equal to 1, it's 0. So the ordinary mathematics, ordinary differential equation we just finished, you cannot apply. That is applying when this function is continuous. When this function is continuous, on the right a continuous function, it never stops. You have to find two solutions and adding them together. But here, if I am writing 0 to 1, and this will be 0 if t greater equal to 1, then no other method to find the solution of this differential equation in which the interval is defined for the input function. So you have Laplace transform left. You have to work with Laplace transform. You are not going to use those methods which we studied in the differential equation. It means Laplace transform solves all the initial value problem which we solve using ordinary differential equation, but it does something new, and that new is it is working when the input function lies in some interval. For example, if I am sketching, this is t, this is 1, 0. So 0, 1, this is t. Point 1 and 1. This is 1. And if t is greater or equal to 0, the function is 0. Look at that. Input function is lying between 0 and 1. That is the thing. And you have to find solution of the initial value problem depending upon that. And Laplace is the only solution for it, which is wonderful idea to solve such problems when the function, input function lies in certain interval. Let ft be a function defined for all t greater or equal to 0. Let me choose a function which is time dependent function and it is defined for all t greater equal to 0. Its Laplace transform is a function f of s given by. So the Laplace transform of a function is the improper integral 0 to infinity. That's why in the beginning I discussed that this is an improper integral 0 to infinity f of t e minus st dt. And if you are solving this integral, you are getting a function in s. We'll see in a minute how different functions are going to be transformed into a function of s. And this improper integral converges because the negative exponential, when s is greater than 0, this function is defined. And on condition on s, s must be positive. If s must be positive, this integral converges and you are getting the answer. So the Laplace inverse is f of t. Look at that. So one of the hint or something I would like to ask, 0 to infinity e k t dt. For what value of k this integral converges? For what value of k this converges? This integral converges for k less than 0. Less than 0. I mean, look at that. Here s must be positive. If s is positive, then this integral converges. This function converges and the whole integral converges to giving you some function f of s. This is. And if I am going to write e minus k t dt, the integral are 0 to infinity. This converges when? Converges if k is positive. Look at that. If k is positive, this integral converges. It means if you are integrating this and putting up a lower limit, your answer must be some definite number. So it means if you are getting some definite value, this integral converges. If not, then this integral does not converge. So this is all about the definition of Laplace transform. It is an improper integral. This function is defined for all t greater equal to 0, and because this is e minus st, s must be positive. If s is positive, the whole integral converges, giving you an answer f of s. And if you are taking the Laplace inverse, you are getting the function back. Laplace transform is linear operator. So Laplace transform is an operator. So it converts a function in the form of t to this domain, and it is linear. Linear, like if you are 2 or 3 functions defining. If you have one function, then you have another function, then you are going to have another function, and you are taking their Laplace transform. You are taking their Laplace transform. Linear mean you are going to take the Laplace transform of the first function, then you have to take Laplace transform of the second function, then you have to take Laplace transform of the third function. So Laplace transform is linear, like differentiation is linear, like integration is linear. So this is going to be example. Find the Laplace transform of the following function. This is 1 t square t cube tn, and this is EAT, this is sine hyperbolic AT, this is cos hyperbolic AT, this is sine omega t, this is cos omega t, etc., etc. So we will have couple of functions to find the Laplace transform, and the whole Laplace transform revolves around these functions. So if you have to find, you should take notice, you should know the Laplace transform of these functions, and then you interpret accordingly and to find the Laplace of the composite function or something. So let me have Laplace transform of EAT. Let me do first of all this. By definition, 0 to infinity E minus st EAT dt. Look at that. The function is EAT this time. And let me write 0 to infinity E. Let me take minus outside, a minus at dt. Look at that. I have taken minus common, then this. It means this integral converges if s minus a is greater than 0. Because this is positive, then this negative exponential will converge for this interval 0 to infinity. So if I am integrating this, I will get 1 over s minus a e minus s minus at 0 to infinity. I am integrating this. Minus 1 over s minus a. Let me have minus infinity. T is infinity. And this is minus. And t is 0. This is 0. This is 1 over s minus a. 1 over e infinity. Let me take this, and this is 1. E raised to the power infinity is infinity, and 1 over infinity is 0. So it becomes minus 1 over s minus a, 0 minus 1, which is 1 over s minus a. So Laplace transform of EAT is 1 over s minus a. Now Laplace transform of 1, which is by definition 0 to infinity e minus st dt. F of t is 1 this time. So I have f of t 1, and then by definition let me integrate minus 1 over s e minus st 0 to infinity, minus 1 over s is taken out, e minus infinity is 0. So e minus infinity is 0. 1 over e infinity and 1 over e raised to power infinity is infinity, 1 over infinity is 0. Minus 1 over s, 1 over infinity minus 1, minus 1 over s, 1 over infinity minus 1, 1 over s. This is 0 minus 1, and this is 1 over s. So Laplace transform of 1 is 1 over s. Let me have Laplace transform of cos hyperbolic at. So can I write in terms of exponential function? The formula for cos hyperbolic at is this. And I have discussed Laplace transform is linear operator. So there are two functions, let half is taken out, and Laplace is working separately on both functions. This half is taken out. Now we are familiar EAT. We have just found Laplace of EAT is 1 over s minus a. So you are not going to again by using definition, you know this, and you are writing 1 over s minus a. 1 over s plus a. Look at that. Straight away you are writing because you have derived 1 EAT and you know that, taking the LCM. S minus a, s plus a. So this is half there. So this is s plus a plus s minus a. A goes 2s. 2s divided by 2 is s over s square minus a square, which a plus b a minus b. I have this. So Laplace transform of cos hyperbolic at is this. Write down the exponential form of the formula and then operate on the Laplace separately because it is linear, and you get it. Similarly, let me have sine hyperbolic at in a minute. Sine hyperbolic, and the formula goes with negative in it, with minus in it. Look at that. Sine hyperbolic, the formula is this, or let you have the Laplace, which is linear, operate on the separately, and I am minus s minus a. Look at that. Once I have simplified, this is s plus a minus s plus a over s square minus a square. This s goes, and 2a cancel with 2, you are left with a over s square minus a square. So Laplace transform of sine hyperbolic at is this. Let us have the Laplace transform of sine omega t. We know that e iota theta is cos theta plus iota sine theta, which is the Euler's identity. Euler's identity. Let me replace theta by omega t, which is cos omega t plus iota sine omega t. Now sine omega t is the imaginary part of it. If I am writing sine omega t, which is imaginary part of iota omega t, this I know. If I said I have, this is the imaginary part of e iota omega t. Let me take the Laplace now. Sine omega t is equal to imaginary outside Laplace of e iota omega t. Imaginary outside. Now I know Laplace transform of EAT. Laplace transform of EAT 1 over s minus a. This I know. And I am writing 1 over s minus iota omega. Since iota is in the denominator, you have to rationalize. You have to rationalize s plus iota omega over s plus iota omega, taking its conjugate and multiplying divide by the conjugate of it. Then imaginary there, s plus iota omega there, denominator a plus b, a minus b, which is s square minus b square, and iota square is minus 1. So it is s square plus omega square. You have simplified this. Now since I am in imaginary zeta, choose the imaginary part of it. So Laplace transform of sine omega t is equal to, I am taking the imaginary part, which is omega over s square plus omega square. This is the Laplace transform of sine omega t. Similarly, if I can write Laplace transform of cos omega t. What do I do is, I have cos omega t, which is real part of this. This cos omega t is the real part of this. And if I am writing real there, I have choose the real. And real part is s over s square plus omega square. This I have with the imaginary. If I am writing real, RE here, so I have to choose the real part, which is s over s square plus omega square. So, couple of more. Let me have Laplace of t. By definition, 0 to infinity t e minus st dt. Look at that. I am integrating this. This is the polynomial which is taken to the first function, integral of it. Let me write first function, integral of the second, minus integral of derivative of first, which is 1, integral of second, minus st minus s dt. This I have integrate by parts with polynomial is taken to be the first function. Now let us have this. Since this function is defined for all t greater equal to 0, because of this infinity, this whole part vanish. If I am putting t as infinity, So this is negative infinity, which is 1 over infinity, which is 0. And for lower limit, this function is going to be 0. So upper lower limit will give you this part 0. If I am finding limit, t approaches infinity, t est. I am applying the limit over it where t approaches infinity and see whether it is 0, yes or no. Infinity over infinity form. Infinity over infinity form. Because t is infinity, here infinity. So if it is infinity over infinity form or 0 over 0 form, what you do is you have to apply Hospital rule. Hospital rule states derivative of this, which is 1, and derivative of the denominator, which is this. And applying the limit again. So this is 1 over infinity, which is 0. It means this part vanish if you are putting the limit t infinity, and because of 0 this, if you are putting 0 there, so it vanish. So upper lower limit will give you this part 0. Minus and minus plus 1 over s there, 0 to infinity e minus st dt. So we have just discussed this is Laplace transform of 1. We have find the Laplace transform 1, which is 1 over s. 1 over s and 1 over s. This is 1 over s square. So Laplace transform of t is 1 over s square. Because this is by definition Laplace transform of 1. Now Laplace transform of t square by definition. 0 to infinity t square e minus st dt. Again integrate by part, treating t square as first function, integral of second minus integral of derivative of first, integral of second. Again, this is going to be vanish by applying upper lower limit. Look at it. Upper limit, this is going to be 0 whether you are applying Hospital or you see this function is defined for this negative infinity will give you 0, and lower limit because of t 0. Minus and minus 2 by s is outside because the variable is t. So that should be inside the integral sign. So what is this? What is this by definition? Laplace transform of t. Laplace transform of t. Look at that. This is Laplace transform of t is 1 over s square. So I am writing 2 over s into 1 over s square. This is Laplace transform of t. So this is 2 over s cube. Laplace transform of t square is 2 over s cube. One more and then we generalize. Laplace transform of t cube by definition. 0 to infinity e minus st t cube dt. Again integration by parts, treating this as first function, integral of second minus integral of derivative of first, 3t square, integral of second dt. Again, this integral vanish by using upper lower limit. Plus 3 by s is taken out, 0 to infinity t square e minus st dt. So what is this? This is Laplace transform of t square by definition. Laplace transform of t square, which we have Laplace transform t square 2 over s cube. So this becomes 3 over s, 2 over s cube, which is 6 over s4, or it could be written 3 factorial over s4. This is Laplace transform of t cube, 3 factorial over s4. Let me write down the summary because the whole Laplace transform revolves around these functions. Summary. Laplace transform by definition is equal to 0 to infinity e minus st ft dt, and this is a function of s. Then Laplace transform of 1, Laplace transform of t, Laplace transform of t square, and Laplace transform of Tn, where n is a positive integer. This is 1 over s square. This is 2 factorial over s cube. Laplace transform of t cube is 3 factorial over s4. N factorial over s raised to the power n plus 1. This we have tried. Look at that. T cube 3 factorial over s4, and then Tn is n factorial over s raised to power n plus 1. Laplace transform of EAT 1 over s minus a. Laplace transform sine hyperbolic AT. Laplace transform cos hyperbolic AT. Laplace transform sine omega t. Laplace transform cos omega t. So sine hyperbolic is a over s square minus a square. This is s over s square minus a square. This is omega over s square plus omega square. This is s over s square plus omega square. So this is the summary. So before going to the next, you should remember this either by heart or by practice, because whenever you have to find a couple of Laplace transform, you are applying these formula. Example, find the following Laplace transform. T plus 1 whole square. Suppose t plus 1 whole square, you have to find Laplace transform. Now you do not know t plus 1 whole square's Laplace transform. What do you do is you have to take the square over. T square plus 2t plus 1. This is the square. And now you are taking the Laplace transform. So since Laplace transform is linear operator, so you can have Laplace of each term separately. Laplace of 1. Now you know Laplace of t square, 2 factorial over s cube. 2 is outside. Laplace of t, 1 over s square. Laplace of 1 over s. This is the answer. And on the left, you are writing f of s. So Laplace transform of t plus 1 whole square means you have to take the square open and then you can work with it. Let me have again one more. Sine omega t plus theta, for example. Find the Laplace transform of this. What do you know? You know only these things. You know only these things. You are not knowing the Laplace transform of sine omega t plus theta. What do you do is, let you have the identity. Sine omega t cos theta plus cos omega t sine theta. Now taking the Laplace. Once you are taking the Laplace transform, cos theta is some constant taken out. Laplace transform of sine omega t. Then sine theta is outside. Laplace transform of cos omega t. This you are going to do is, and you know the Laplace transform of sine. You know the Laplace transform of cos omega t. Putting there the value and getting the answer. So cos theta as it is, sine omega, omega over s square plus omega square. Sine theta here, this is s over s square plus omega square. So this is the answer to find the Laplace transform of the function. Because you do not know Laplace of this whole, you have to convert it into elementary functions. And then, because what you know is this, you know this, and you are not knowing anything else. Let me have one more. I am writing sine square t. This I am writing. Find the Laplace of sine square t. You do not know. You know the Laplace of sine omega. But you do not know. Just half angle. 1 minus cos 2t divided by 2. Applying the formula. So convert into half angle. Once you convert, then this become half. This become half minus half cos 2t. Now taking the Laplace transform. Once you simplify it into the simpler function, Laplace of 1. Let me take half is outside. Minus half is outside. Laplace of cos 2t. So half is there. Laplace of 1 is 1 over s. Minus half is there. Laplace of cos 2t. Cos 2t means cos omega t. Omega is 2 this time. Omega is 2 this time. So this is s over s square plus 4. This is going to be the Laplace transform. So whenever the something given, you have to interpret into the simpler function whose Laplace transforms you know. You are not going to have sine square can be written sine t into sine t. No, you cannot do this. You have to interpret into half angle and then separate it. And since Laplace transform is linear operator, you can take the Laplace separately and getting the answer.